Do you know how the avalanche breakdown will happen in the BJT? So even you guys have already know about how the avalanche breakdown will happen in the diode. So if you guys need to know how that is happening in BJT, please pause this lecture. So where we can detailedly discuss on these things. So last class we have detailedly discussed on the early voltage. So early voltage or early effect. So that is the criteria that we have to take into account. So whenever there is an effect that is happening, because of that the effect is nothing but whenever we are keep on increasing the reverse bias voltage, the slope will keep on increasing. So there is one condition when the WB, that is the actual WB, actual width of the base potential, which is going to 0 or which is proxy equal to 0, that condition is punch through. So this punch through won't happen that much easily, because before this punch through is happening, the BJT will be going into avalanche breakdown. So BJT will be going into breakdown. So breakdown means what? That is damaged. So then we can't work in that BJT. So that is the thing. So how the avalanche multiplication will work is that when the VCB or the reverse bias, which is keep on increasing, the energized electron will be generated. So energized electron will be there. So energized electron in collector terminal. In collector will hit the majority charge carrier, will hit the other charge carriers. So because of this effect, the 1 will become as 2, then 2 will become as 4, and 4 will become as 8. So this what will happen? IC will keep on increases. If the charge carriers keep on increasing, then the BJT will be damaged. So that is what the thing that we are discussing here. So even in the diode we have detailed discussed things. So if you have any doubts, please go and watch that. So let's see how this effect are calculated in the reverse characteristic, the output characteristic curve. So we know in the linear region it will be acting in a straight. After the linear region, some saturation will happen. So because of the effect of early voltage, this will be having some slope. So this will be some 8 or 10 degree of slope. Okay. So if the VA or if the reverse potential is increasing, keep on increasing, then what now? The VA will be keep on decreasing. So VA is keep on decreasing, the R0 will also keep on decreasing. Then there is some problem that will be happening there. So in order to avoid that thing, so this the punch through will hit. So punch through is affected. We know the entire depletion region that is affected by the reverse. That means entire depletion, not the entire base width is affected by the depletion region. But that will not happen. Before that, the avalanche breakdown will happen. So after the avalanche breakdown, the charge carrier will increase tremendously, and that will be going into breakdown state. So this point, so where the breakdown occurring, right? So where the breakdown is occurring, so that point is termed as the breakdown voltage. So that is VBR. So that is a BR is a breakdown voltage. So this is VCB and this is IC. So this is the characteristic curve. The slope is because of early effect. So after this point, then the breakdown will occur. So let us discuss how the breakdowns are calculated and how that is contributing to the thing. So let me take another one scenario here. So this is with VCB. So let's take another one, that is VCE. So okay, so let me replicate this diagram. Okay, fine. Okay. So this is VBR. So let me take this as a VCE. So this is VCE condition. This is IC. So this is IC. This is VBE. So this is VCB. Okay. So this is what the condition. So here we are taking two different characteristics. Okay. So this is the characteristic curve of this breakdown voltage is there, right? So this breakdown voltage can be also named as BVCEO. This can also be named as BVCE. VCBO. Okay, so let me explain what the thing is that. So VCEO, which can be stated as the breakdown voltage. So which is the breakdown voltage at reverse bias collector junction. Reverse bias collector junction in common emitter mode CE when base is left open. When base is left open. So this is one of the very important definition, guys. So we have to remember. So VCE. So the CE can be taken as a common configuration mode, and this one, the first term is there, right? So that is called as a junction, and the term which is not here, the collector base or which is not here, that terminal will be left open. So means the condition is that where IB which is equal to 0. So here the terminal which is not here is the IE. So IE will be equal to 0. So this is what the point that where this voltage will be calculated. So you guys need to know. Similarly, ICEO, ICBO is also important. So the general representation, the VBCEO, which is equal to VBVCBO at the difference of 1 by beta 1 by n. So this is the term of differences. The n will be usually from 3 to 6. Okay. So for an example, if beta which is equal to 100 and n is equal to 3, then VCEO which is much less than VCBO. So usually common base breakdown voltage will be quite higher. So that's why in majority of the cases they will prefer some common base configuration. So this is the early effect on how the breakdown, avalanche breakdown will be maintaining the device to go through punch through state. So punch through state is also similar to the breakdown voltages, but before that the diode will be going into damage state. So that is what we are taking into account. So let me write the three different comparisons. So not a comparison, how the configuration diagram can be wrote here. So let me draw the thing. So common base. So here is the thing. So this is the common base. So this is how the diagram will be represented. So usually when we are drawing circuit, right? So on the time we will be drawing the things like that. I haven't drawn it properly, so let me redraw it. So this is okay. Okay, so this is how you usually represent. So thing is that, so this is E, this is B, this is C. So if it is an NPN transistor, P to N the current need to flow. So arrow will mark like this. It's a base to emitter. Okay. The supply will be usually here it is a forward bias. So this is negative bias. So negative supply, positive supply. So which is named as VBE, and here it will be negative bias, reverse bias. So here positive, here negative. So this is VCB. Okay. So this is with the VCB configuration. So here this is common base. So current gain formula will be alpha. So here how can be represented is the so this is how the configuration can be represented here. So this will mention like this. This will be used to do grounded or any kind of potential that will apply. So that is not a problem. So this is base, this is emitter, this is the collector. So this is something pointed outside, means this is NPN transistor. Okay. So this is forward bias, so minus negative, so which is VBE. So this one is reverse bias, so which is VCE. Okay. So I hope you guys are able to understand. So common collector, so which is same configuration as this one. If you see, this is collector, so this is collector, this is emitter, so which is base, right? So here things are, so this is we are taking NPN transistor. So arrow is marking like this way. So this is what thing. So here this will be gamma, and here this will be beta. Okay. So these are the three grain formula. So beta will be equal to alpha plus gamma. So this is one of the very important relation that you guys can remember. Okay. So from here, let us draw one more relationship. That is, we know that alpha which is equal to IC plus IE. So which can be also written to IC divided by IE can be written as IB plus IC, right? So 1 by alpha which is equal to IB plus IC divided by IC. So which can be divided. So that is 1 plus IB divided by IC. So this one IB by IC, which is equal to 1 divided by beta. So this is 1 plus beta divided by beta. So we know that beta, which is equal to IC divided by IB, right? So from that only we have taken this. So if we take the thing, so 1 by alpha, 1 by beta. So if we take the reverse of this thing, so we know 1 by alpha, which is equal to 1 plus 1 divided by beta, right? So if we take the negative this 1 to the side, so 1 minus alpha, which is equal to 1 divided by beta. So which can be written as 1 minus alpha 1 divided by beta. Okay. So beta, which is equal to alpha divided by 1 minus alpha. So the relationship between alpha and beta is this one. So you have to remember this thing. Okay. So alpha, which is equal to beta divided by 1 plus beta. So anyone you can remember. So I usually prefer this one because alpha beta divided by 1 plus beta. So this is some quiet thing we can easily remember. So from here we have discussed all our technical analysis, all the shortcuts, all the things, just like everything. So next class I will be solving few problems there, so that we can wind up our understanding on all the BJT. So in BJT what we have seen is that how the current flow. So that is only the thing that we need to focus on semiconductor devices. Apart from that, we have detailed discuss on early effect, so other avalanche breakdown condition and other doping and size configuration, those things we have detailed discussed, and some IB, IC, those configuration and each diagram. So how we can represent NP and PNP, everything we have detailed discussed. So I hope you guys able to understand few things and able to be in phase with me. So if you guys have any trouble or difficulties, please post in the comment section. I will be there to solve all things. So there is one more lecture that we can complete our BJT, like a problem discussion. That will be the next lecture I will be posting. So stay tuned guys. So please try to solve. So come up with calculator paper for next classes, so you guys can able to solve that one. Thank you guys.